1, 2, 3. Excellent. Good morning. Is this on? Excellent. I'm very happy to see all of you here. I hope you had a great start of the conference. My name is Oleg Šelajev, and we're going to talk here about GraalVM. And this session specifically will be about the optimizations that the Graal compiler, the main component of the GraalVM, excels at, right? So I work as a developer advocate for Oracle Labs, which is the main moving power behind the GraalVM project. It's a research and development institution at Oracle. And if you have any questions, or you want to find me in the internets, or you want to, I don't know, ping me and say something doesn't work, or just vent about how miserable life of a developer could be sometimes, I'm there for you. I go by @Šelajev. You can find me and talk to me. So before we start, as always, please do not make any forward-going business decisions based on the contents of this presentation. That is really important. We'll talk about GraalVM. It's a high-performance, embeddable polyglot virtual machine that can run programs in many different languages. Not many, but like in several different languages currently. So just before this talk, I had a session about like an introduction to GraalVM in general. Who was there? Okay, another question, who wasn't there? Okay, so more or less half and half. I'm going to repeat some things about the general introduction to that, so bear with me. If you hear a joke that you heard just 1 hour earlier, please laugh. It really is important for my well-being and ego. So GraalVM is a high-performance polyglot virtual machine. It's a drop-in replacement for normal JVM, so you can just download a binary and replace your path and your Java home with links to the Java executable inside the GraalVM distribution and run your Java programs. Why would you do that? Mainly because it is a state-of-the-art thing that can run Java programs and programs in JVM language really, really fast, which means often faster than the normal JDK distribution that you are using. So say if you're using OpenJDK or Oracle JDK or any of the forks of OpenJDK which are available, we replace the compiler inside the JVM with our own implementation, plug it through the JVM CI, and that compiler is really, really good. And it's written in Java, and it excels at certain optimizations, high-level optimizations, and it will become even better with time. First, because it's easier to write programs in Java than some native languages. So it's easier to evolve it. And then because we have certain high-level optimizations already covered. So fast runtime for in place of JVM. It also can allow you, the GraalVM as a project can give you the opportunity to run certain Java programs in a standalone mode without the dependency on the JVM, where we compile it ahead of time using the same compiler, but not as a just-in-time compiler, but as an ahead-of-time compiler. And then the result is really fast to boot, and it has really low memory footprint. You can run a microservice under like 10 megabytes of RAM. Like it's a small microservice, but it's still 10 megabytes of RAM is really not much. And you can embed all this goodness and use different programming languages to execute on the JVM and on the GraalVM in a single context. So the current ecosystem of GraalVM and what it supports is this. On the top, you can see a number of languages, and we support them, right? So there are JVM languages in one big family. There are JavaScript, which actually includes a Node.js API, Ruby or Python in different stages of compatibility. So JavaScript is top-notch, right? The compatibility of the JavaScript implementation is compatible to modern browsers and the actual Node.js implementation. So I think it supports JavaScript standards, ECMAScript for 2016, 2017, and some features from 2018. And it's really like much easier for us to be compatible and add new features because of how the support for languages is implemented. We just need an interpreter for the language, which is kind of in just a Java program. We don't need to figure out how to map and compile the language to the lower level. So there is no mapping between JavaScript concepts and the Java bytecode or machine code. There is just an interpreter for that, and we compile that ahead, like, just in time to a very efficient compiler automatically. So those guys are supported, and then there are native languages for which we support the execution through LLVM. Anything that compiles to LLVM can run on GraalVM through that interpreter, and at runtime, it will be optimized just in time using the Graal compiler to be efficient. And now, all those languages can be executed in different modes. So in the normal thing here in the corner behind this table, you can see or cannot see the OpenJDK. So normally, if I would say like something runs on GraalVM, I would expect, I would mean that it runs in the context of the JVM. So it will boot the JVM, it will start the JVM, it will plug Graal compiler as a just-in-time compiler into the JVM, and then it will use the normal virtual machine for that. So in fact, the GraalVM distribution itself is an OpenJDK build where we replace the compiler with Graal compiler and then add other things to support other languages. You can run all those in the context of Node application, and just like with JVM, this would be a normal Node application, binding to all the signals handlers and doing all the normal Node stuff. It will have the event loop, so your normal ecosystem of Node applications will run there. GraalVM is embedded in certain builds of Oracle database, which is great because it's a very important database in the world and inside Oracle specifically, which means that you can run languages, those languages and programs in them inside the Oracle database. So for example, you can run stored procedures written in JavaScript. You can run JavaScript as a stored procedure inside the Oracle database. And behind the scenes, the Graal compiler will compile that just in time during the runtime, right, to collect the profile and optimize it at runtime inside the database. So it's the same as about MySQL, and you can compile programs ahead of time into a standalone binary. So the common thing here is that there is one really amazing compiler written in Java that can be used in different contexts and in different ways, right? So it can be used ahead of time, it can be used just in time, it can be plugged into different runtime systems. So the all components that a normal like execution environment should provide, like a garbage collector or thread shadowing primitives or code caches, everything that a JVM does for Java programs, those can be plugged from outside, right? So when we compile to native image, there will be a thin implementation of a virtual machine that does garbage collection, but it still will be the same just-in-time compiler. So it gives you a number of degrees of freedom, so you can choose the languages and the tools that fit the problem the best. For example, Python is known for machine learning currently, and JavaScript is known for, among other things, how incredibly large the ecosystem is, so you can find code that solves whatever problem just by browsing for it, and then you can glue it together with all other languages. So, but what I want to say is that the central piece is the Graal compiler. And today we're going to talk about it. There are a couple of other sessions here at the conference, so if you want to learn about the native images specifically, then later today, Andrew will be talking about the Micronaut, and this is a new framework for the microservices for Java, and that works with GraalVM, and you can compile that to native image. So he will do, maybe he can provide some background on the native images if you're interested. And then tomorrow there is a session by Chris Tallinger from Twitter. Twitter is using Graal compiler. I think I have a slide about that, but I might as well just go with it now. They're using the Graal compiler to run their production services. So they're using that in production. Every time you tweet, there's a part of code that was generated by the Graal compiler is responsible for that. When you see Twitter is down, that something else is at fault. Probably. No, they're using that for a certain time. They see benefits. They see the performance boost and increase. They save money on the cloud bills. And it's, in general, a good thing. So if you're interested about that and how to run Graal compiler in production, I think that would be the most insightful session about this. But we're going to talk here about specific optimizations. So I'm going to show you some benchmarks. Hopefully, they will run well on this poor MacBook. We'll look at some numbers, and I'll try to explain how that particular optimization works and when it's particularly beneficial. Right? So the goal, let's go further. So this is the map of the components of GraalVM. We have the runtime system on the bottom, and then so with the JVM, that would be the Java hotspot VM. We plug the Graal compiler as a JVM CI compiler. JVM CI is an interface for the JVM compiler interface. So this is the normal way how you plug a third-party compiler into your JVM. So if you want to write a compiler, you can do that. There is a certain API for that. And you can compile your bytecode at will, or crash, if you will. So with that, Graal compiler plugs into the JVM, and then with that, we can execute JVM languages natively, right? Because JVM will load the classes, find the bytecode, do everything that it needs to do, and then it will just ask the compiler, please compile this bytecode. And the compiler will do something and just say, oh, here's this machine code, right? This is what the compiler does. And then on top of that, there are framework for implementing managed languages and implementations of the languages themselves. So we're going to focus on this part. Who's here a Java developer or writes Java mostly? Who writes non-Java JVM languages? Scala, Kotlin, Clojure? Oh, one person raised their hand on Clojure. Excellent. Love it. It's a Lisp-like language. Opinionated, very elegant. Nice. So we're going to talk about the compiler. Graal itself is an open source project, so you can find it on GitHub. The development, mostly by the GraalVM team at Oracle Labs, is done on GitHub. So the commits go there, the pull requests go there. We try to be as good an open source ecosystem member as possible. You can browse the code. It's all written in Java, so it's easy for Java developers to understand. You can click through it in your favorite IDE and understand what's it doing. If you have an idea for an extremely crazy but very useful optimization, you can hack it in your IDE and test. And it's much easier to adopt as a, from the development point of view, understand what's happening as a Java developer compared to other compilers which are written in native languages. If you want just to run it and execute it and see whether it speeds up things or not, there are binaries available for download. GraalVM team produces those. We have the community edition, which is the open source components built and put on as a zip file on GitHub. You can download that. It is functionally complete, so it can do all things that an enterprise edition can do as well. But there is an enterprise edition which comes with a better compiler. So there are additional optimization phases and different heuristics, and it in general produces faster code, which comes in the enterprise edition. So if you can download and evaluate that currently, getting that from the Oracle Technology Network, which is the place where you get your Java binaries, Oracle JDK binaries as well. So you need to accept a license, but then you get the same zip file, and it's an enterprise edition, and you can evaluate those. They can run the same programs, but that one would be faster than this one. So if you want to adopt it, and if you figure out that, yes, I would like that additional performance boost, and it makes sense for my business goals and my project, then you can, well, figure out how to obtain the enterprise edition and whether you want it or not. But if not, the community edition is something that you can use. Binaries, excellent. So back to the compiler. Now, there are two projects that kind of build a virtual machine, and they're both heavily backed by Oracle, right? So there is OpenJDK, which is a normal implementation of the reference implementation of the Java virtual machine, and there is this new virtual machine called GraalVM, which also kind of claims to be a JVM. So there is quite a bit of confusion between those. Those two are two separate projects. They are run by separate teams. Most importantly, there is difference in vision. So OpenJDK is the reference implementation of the JVM. They value stability, backward compatibility. They have millions of deployments all over the world. They have like a large, I don't want to call it legacy because legacy has like a little bit negative connotation. They have this history. They support the current well, world of an ecosystem of software that currently there is, right? So they move forward, but they are a JVM. GraalVM wants to be the virtual machine for all languages. If you want to run something on your computer, you should run it on GraalVM. That's the vision, right? So that virtual machine will be everywhere. It will be built into databases, web servers, any platform that wants to enhance itself with scripting capabilities, used as just-in-time compiler, ahead-of-time compiler. It is the virtual machine for all languages and all workloads. So, which is a different goal from OpenJDK's. And it's also a younger project. We are currently not even 1.0. It's quite a mature project. It was started 7-8 years ago at Oracle Labs, and there were quite a bit of academic research done and written about that. And now this year we try to package it as an industrial product that people in the community and the ecosystem actually can use and can benefit, well, in the industry, right? Because it just makes sense. So now, currently, we are at 1.0 release candidate 9. We started releasing release candidates back in April, trying to convey the message that we are ready and we feel that we are ready to release 1.0. But also, what is very important is that we would like the feedback from the community. We want people to run their code, to run their workloads, and give us feedback whether it works, whether it's fast enough, whether there are some issues, bugs, or any problems. Because, well, after all, we can run spec JVM and spec JBB only so many times. After that, it works and it's fast, and we need access to larger code bases to see how it works. So we started that in April. We received tons of feedback. We closed quite many issues on GitHub. People approached us, and then now we're here. Personally, I hope that very soon we will be, very soon, like in the next maybe several months, we will release the 1.0. I'm not sure when it will happen, but it will happen. And then we'll get it from there. But the point of this, there are two different projects. They are both good projects, and they're both nice neighbors. So GraalVM takes the JVM implementation from OpenJDK, right? So when you run GraalVM's Java, it actually uses the hotspot, which just compiler replaced. And OpenJDK, what it does, it takes the compiler and adds from Java 10, it adds Graal compiler as an experimental compiler in your OpenJDK distribution. So if you run OpenJDK or Oracle JDK or JDK 10 and later, you can enable a couple of command line options, and boom, you are running Graal compiler, which means your code will be compiled by Graal rather than C2, which can lead to better performance. which might lead to better performance. Not always, but. So this is the community version of the compiler pulled into the OpenJDK forest. It's a snapshot of the Graal compiler, right? So it's not the master, because again, OpenJDK builds and releases are their priority and their task. So they pull at some point of time, they run tests, and then they release when they release, and the development of the compiler in the GraalVM project goes forward. So if you want later fixes, you should consider evaluating or trying the GraalVM distribution. And then it gives you quite a bit of performance benefits for various workloads. Well, we evaluated the stream API performance on a bunch of benchmark. I'm going to show a couple of them today. For high-level abstract code, which doesn't deal with low-level bit manipulation, or for the code that isn't specifically written to be aware of the C2 compiler and how C2 optimizes. So if you didn't manually optimize your code to be really, really fast for the existing compiler, Graal can show quite a bit of benefit. So if you use high-level abstractions like stream APIs, which have like tons of method calls, which are hard to inline for normal compiler, we can be several times faster. If you use other JVM languages, for example, Scala, which is very different. Scala produces very different bytecode patterns and shapes than Java programs, right? So if you're writing Scala and if you compile classes and if you look into those classes, you will normally not recognize the patterns that Java has, because Scala uses different things. So on Scala, we get larger performance boost. The community edition gets something like 10%. The enterprise edition gets something like 30%, 35% performance increase. And this is great. So the reason for that is the Graal compiler. So we're going to start. And I'm going to show you a couple of demos. And I'm going to show you how to maybe assess what is happening behind the curtain under the hood of the compiler. Imagine you have a class like this. You have a demo class, and you run it, and you want to see how it's compiled to something. Who knows how to see what it's compiled to, and whether it's actually compiled or not? One person. Who doesn't know how to check what's compiled to? No, this is fine. Like, it's OK. Who doesn't know how to figure out which machine code this will? Oh. What happened? Was it me? Did I do something? Who said yep? I didn't do anything. Gather windows. No, how do I mirror arrangement? Was the presentation there before, like this 20 last minute? Excellent. Excellent. Yeah. What do we look at? The demo class. So who doesn't know? Who knows how to figure out which machine code and whether the just-in-time compiler compiles this code when you run it? OK, I will assume the rest doesn't know, because it's hard to admit when you don't know something. So there is no shame in that. We have a class. We can compile this class using Java C and get the bytecode, and then we can feed that bytecode to the Java executable and see what it's doing. So I will show you. This is not it. Yes, this is it. Weird, but I can take it. So I've downloaded the GraalVM distribution, and my distribution is a normal JDK-like thing, right? I have my Java command here, and I have my Java C, and so on. If I do which Java, you can see that I'm going to be using this Java, right? So my Java will come from the GraalVM distribution. And it's an enterprise edition, because I'm evaluating here. So what it makes sense to do is to evaluate for what is possible rather than what's free, because that's how proper science works. So I'm going to use this, and where's my, I had a different thing here. Yes, excellent. This doesn't need, this is it. This is my class here. I have my demo class here and my Devoxx Java, so I just created and I compiled that normally. And then I will run it, and I will actually show you what I will run. I will use a couple of command line flags to help me to see what's out there. I will use print compilation, and I will just say that I would like to compile my my workload class. So I will not even just run those two. I will run this run thing, and you can see that my output here tells me that that method, they were compiled. So if you're running something and you are wondering whether the Graal compiler actually compiled something or not, you can use a couple of flags to see that. If you add back those two guys, so this is unlock diagnostic VM options and print assembly. And if you're using like the Graal compiler inside the OpenJDK distribution, right? Not the GraalVM distribution, but if you use normal OpenJDK, you will need to enable the JVM CI compiler. So first, those two will let me just run it again. They will actually print assembly. How many of you read assembly code weekly? 3 people. Excellent. That's more than me. I read it once a month, just to keep myself in shape. No, I don't read it much. I can recognize assembly when I see it, when it stares at me from the screen, but it doesn't tell me much. So to obtain this, if you just run those on a normal JVM, you will not see the assembly code, right? You need a certain hotspot disassembler library, HSDIS, and you can obtain that, or you can build that yourself and just put it in a certain folder in the JDK, and then you will be able to see assembly. I'm not sure this helps normal Java developer much, but it gives you tools to see what is the actual end result of your compilation, right? So if you're running something, you're running a benchmark, and you don't believe your eyes how amazing that benchmark is, the results, you can look at the assembly code, and that would be the ultimate truth. So those are the things. If you're running the normal JDK, then what you need to do, you need to enable certain options. This is enable experimental VM options. This will enable options which are considered experimental, and Graal compiler is an experimental compiler in the OpenJDK, and then you just use and say, use JVM CI compiler. Normally, you would also need to provide like a path to a jar file which specifies the compiler, but since at the current moment of time there is only one external JVM CI compiler, which is also available by default, just enabling that will make it work with Graal. So those bunch of flags, and you can experiment with the workloads and see whether your application under test or your benchmark runs better with Graal compiler or not. Excellent. Now I'm going to show you I'm going to show you this benchmark first. This is something that I showed before. No, I will show you a different benchmark first. Where's my different benchmark? Yes, this one. It's a very simple benchmark written with Java microbenchmark harness. It takes a bunch of integers, and it applies stream operations on top of that. And I'm going to run this, and I'm going to disable the JVM CI compiler here. So let me just start it. It should run from here. Something is not right. Let's run it from the command line then. Damn it. I tested it yesterday. Sorry about this. We'll figure out about that later, but we'll see because there is different benchmark. But I just want to run this and tell you Java minus version. We have the Graal compiler, so I will run it without Graal. Run, no Graal. Excellent. We are disabling the GraalVM CI compiler, and it will run it now. Run, no Graal. We're going to run that benchmark, and we'll see the numbers. So why I'm running this benchmark? Because I want to show you that, first, Graal compiler can optimize code, at least for certain snippets of code that you can see here, because otherwise it would be really hard to understand what we're talking about, because JVM is a state-of-the-art virtual machine, right? It's hard to beat the JVM. But I'm going to show you a small example here, and I'm going to show you then different benchmarks for particular optimizations where Graal compiler excels and is much better than C2. So we're going to look at the escape analysis. We're going to look at the inlining and the polymorphic inlining, and maybe vectorization if we have time. So those are the benchmarks, the optimizations that actually benefit when those are really good in Graal. So when the code is, when you're running code where those optimizations could lead to the largest benefits, it will run on Graal much better, right? So if you are allocating objects, escape analysis could probably eliminate those allocations, and a better escape analysis is a very high-level optimization. So probably it will run better with Graal. So now I'm going to run this with Graal, just to show you that it actually runs better. If you're running highly abstract code that uses multiple method calls or uses stream APIs, where it's hard for the C2 to optimize that, then the better inlining together with escape analysis and the polymorphic inlining will provide you with quite a bit of benefits. So you know what? I'm going to do this. Not sure how to do this properly, but I will just make it better. Now you actually can see the numbers. So you can see that currently we have, with Graal, this benchmark is running in 10 nanoseconds per operation, and without in 180. So the result is outstanding, and this performance boost, you cannot expect that on any application. Right? So if you run large Java applications, especially optimized for existing just-in-time compiler, then probably your results will not be this. But on certain code patterns, you get quite a bit. So why is it here? And this is a number of optimizations. Escape analysis, because we don't allocate and don't auto-box objects here, because we operate on small integers. So normally when you pass it to methods, they will be converted to large integers, which means an object allocation. And then actually we can just inline all of this into a single thing. So I'm going to show you a quick look how it looks behind the scenes. So the JVM CI compiler, which I talked about, there is an interface. It's inside the JDK. It gets the compilation request and returns a result. You can think of this as whether this would be a byte array and this would be a byte array. Takes the byte code and returns some machine code. Not exactly that, but is approximately like this. And internally, the Graal compiler operates on the internal representation, which is the program dependency graph, kind of similar one to which C2 uses, but a little bit different. And there is a way to instruct Graal compiler to output those graphs. And what you can do, you can look at them, and you can understand what's it doing, and you can see how it optimizes large graphs into smaller graphs. So you can see the results if you want to. So if you have a simple code like this, and this is the piece that we had in the workload, similar, the program graph will be like that. So important things is here, just one thing to remember. The red lines mean control flow, so this is how the program runs, and the blue lines mean data dependencies. So this is the data that flows through the graph, and the red ones are the control flows, your if statements, and so on. So for simple programs, it's kind of easy to understand. We start, then we have the division here. Division takes the result of constant 2 and plus operation takes 2 parameters that we pass as method references. And then we divide them, and then we return them. Simple. If we look at a little bit longer code, which was a for loop, then immediately it gets kind of messy. The same concept applies. Red is the control flow, blue is data. And you can actually, if you look at that, you can figure out things which make sense. There are loop start and loop ends. There are checks for array lengths. There are arithmetic operations. But in general, if you're not a compiler developer, probably you will not look at those things. But it's very important to know that they are there. So when you get to the problem, or when something doesn't run fast enough, you can troubleshoot that, or at least submit an issue correctly. Not correctly, but in a most useful way. So if you're running Graal and you don't feel like it does everything that it should, optimization-wise, what you do? You disable it and see whether C2 actually produces a better result, because sometimes it doesn't, and then that's the thing. You figure out the keys to print the compilation and maybe trace certain de-optimization things, because Graal speculates quite a lot about the execution. So at a certain point of time, it can de-optimize based on the profile. Sometimes it gets complicated there. And then you can dump the IR graph, and then you can send it. You can look at that using the idea graph visualizer thing. It's a command line utility, but it's more of an interest rather than actually useful for a normal developer. Excellent. So this is now the demo, right? Yes. So back to the demos. We looked at this benchmark. It was really good for this arrays, and let's try to understand on different benchmarks why is it good. So let's look at the partial evaluation. Imagine you have a code like this. You have a class. You have a class that takes quite a bit of space. And then you have some code that uses that class and instantiates objects of that class and uses them. But not always, right? Sometimes it uses them, and sometimes it doesn't use them. So this is where the escape analysis is great. So let me just run this. I will run this, and I will edit configuration, and I will, what do I do this? Just normally. I will use this, and I will disable the compiler. Just because I want you to show without Graal first. And this is not a proper benchmark. We just instantiate and call that method plenty of times and just give it a different Boolean condition once in a while. Right? So most of the time, we will not hit this if block here. But sometimes we will. Yes, are we running? We are not running. Stop it. Run this. Foo. Run. Edit configuration. OK. Fantastic. We started, and it runs. So with the Graal compiler disabled, we see the results something like 14 milliseconds, 14 seconds. It does quite a bit of loop iterations here. Come on. Come on. 16 seconds. Now, if I enable Graal, the escape analysis in Graal compiler is different. It's a practical approach, which means that it doesn't have to prove that the object doesn't escape ever, right? So this is where we assign this newly created object to a field, and from that field, somebody can read this object, right? The object escapes, a different thread can see that, or a different piece of program can see that. If we don't write it to that field, this object cannot be reached from any other place in the program, right? So theoretically, you can not create this object until later it's needed, right? And you can work on the primitives, or here currently actually do nothing if we think that the condition will not be met. So when I run this with Graal, and to do that, I just need to disable this. I will disable that by prefixing with -d, making it an irrelevant property. Then it runs much, much faster. Why it runs faster? Because essentially what it does for me, Graal actually runs this program. So when the condition isn't met, my object is not created. However, when the condition is met, my object is created on that branch. So if you imagine like just a tree that we evaluate for the program, then on one pass, if we can prove that on one pass the object isn't needed, Graal can eliminate that allocation. And you can see that if you run a bunch of GC parameters, and you can see the results for the GC allocation and number of garbage collection options, and so on. I'm going to show you another benchmark for the escape analysis algorithm. This is my matrix multiplication. This is actually a proper GMH benchmark. What it does, it multiplies complex numbers, which are an immutable data structure. I'm going to run this, and you can see the actual benchmark multiplies some numbers. So there are 3 layers deep for loop, and then we do those operations which create garbage all the time. So what I'm going to run it with the GC profiler, right? So this is the GMH option to actually profile garbage collection and memory allocations. And I will first disable the compiler, and I will run it. Sure, what was that? Yeah, because it runs JDK 11. I don't want JDK 11. I want Graal. I want my GraalVM. Run. Excellent. We run. We are good to go. So this benchmark was taken from the presentation where somebody showed the Valhalla project, right? So in the future, we'll be able to pack data very neatly into memory, and thus it will optimize and run faster. And I just wanted to show that currently, with the more sophisticated compiler, you can essentially run it faster. Not as fast as with Valhalla, probably, but much faster than normally already right now. So essentially, so we can see the result. We have this general score is 77,400 time units for operation. And what you want to see is the allocation rate here is 4,000 megabytes per second. And the number of garbage collection runs throughout the iteration. So 300 garbage collections. Now, I will run the same thing with Graal enabled, and we're going to, most importantly, look at the number of garbage collections. Yes, so we did the GVMCI disabling, and now we will run it. It's weird because it's not, yeah, because I didn't run it like that. I disabled here. Excellent. So we're going to rerun this. But now we will not disable the Graal compiler. And look at what the garbage collection numbers are saying here. So essentially, what I want to show you, that this complex number is not created, and those intermediate results for the next new complex numbers are not created. And it just all operates on the primitives here. It will take a little bit of time, 40 seconds, and it will run. So when is this useful? When it actually you can make use of the escape analysis being better, besides just running your programs faster? Very often you write code defensively against the compiler, right? When you write logging statements, when you use logger, what do? You check if a debug log is enabled, and then you write the line that says, oh, debug this. Why do you do this? Because normally, you want to pass the parameters. Normally, that logging method will take the var args, which means that your variables need to be packed into an array, and then that array will be used or not. So, and that will be done prior to the method invocation. So what you want to do on the code level, you want to disable that and like prevent that with the if block, right? So only if it's enabled, you're gonna call it, which makes sense from the performance point of view, but it doesn't make sense as well, because if your compiler would be smart enough to optimize that like object allocation and array allocation away, then you wouldn't need to pollute your code with this semantically irrelevant if block. Because what it does, it checks if the debug is enabled, then it calls the method, which itself also checks whether the debug is enabled, right, inside its own implementation to figure out if it needs to print something or not. So you're doing double work. You have to be mentally aware all the time about that, but it's actually compiler's work to optimize that way and to make the code that you want to write actually run fast. Okay, so we ran this benchmark while I was talking about this. We can see that the score is almost twice as low. It was 7,000 something. And now, the most importantly, there are 4 garbage collection cycles throughout this thing. So before it was 300. So the main performance difference here is from not allocating objects all the time. I have a benchmark example here, which actually does exactly this thing that I was talking about kind of with the logger. So when we allocate and check arguments and pass some var args to a method, which takes the var args, and we only consume that under a condition, which we also pass, right? So I'm not going to run this currently, and this benchmark wasn't even created by me. It was by Vladimir Dolzhenko, and I just took it from his blog post. And the results for that, I'm going to just show you the results for that, is that we allocate much less with the GraalVM, with the Graal compiler, rather than without the Graal compiler. And that improves the performance score as well. You can find that. I can link you to that, and you can run it. But the important bit is that you can run this methods like that without adding the condition on top, like here, right? And it will still be fast and performant. So what I want to say is that with a sufficiently smart compiler, you should be able to write code as you want, as it's normal for a developer, rather than to create custom kind of exceptions and code patterns that you would do only because the compiler is not smart enough and sophisticated enough to optimize certain things away. So the escape analysis has immense benefits. Other things that have really good benefits, especially, so if we look at back at this benchmark with the streams API, right? So what we do here, we apply the same method, and the implementation of those abstract methods are in different classes, right? So typically that would be when you have stream APIs, because you have the actual like in-stream and like normal stream and hundreds of classes which actually implement the stream API. Also with the collections. So when you actually call those, you get the polymorphic calls, right? You have one call through a single method definition, but actual implementations are different. So it's harder to inline that versus the case where you have just one method signature and one implementation. Because there you can just say, OK, I call this method. This is my implementation. I can take that implementation and put it into the method caller, right? So I inline that, and then it's very simple. But if I need to check which implementation I need to pick all the time, it becomes much harder. So I'm going to show you this polymorph code. And we're going to run this with a bunch of things, a bunch of times. We have an interface, which is an operation, has one method. This will be our target for the polymorphic inlining. We have different implementations of that. So there is addition, there is subtraction, and there is the bitwise OR. So those will be our implementations. could be, if you think about collections library, could be list, set, and map, and you called normal methods like contains or get, because any program will use a collection API in some sort of form or shape, and every collection API usages will probably consist of checking whether an element is inside a collection and accessing them, whether random access by index or by key or something, right? So what we're going to do, we're going to run this, and first we're going to pollute the profile conditionally. And by polluting the profile, what I mean is that we're going to call this bar method, which just applies the past operation. We're going to call it with one operation and the other operation for a bunch of times. So here, we have all three operations here in an array, and we're going to interchangeably call, so the first one and the second one, subtraction and OR. So we're going to pollute the profile. We're going to make sure that the JVM thinks that we're going to mostly call those two. And then initially and unexpectedly in the main loop, we're going to actually call the third operation here, which is add. We're going to make it very unexpected for the just-in-time compiler, because we kind of train it that we're going to pass it just two operations, and then we suddenly change what we are doing. This happens in real life way more often than one could think, and it's really not easy to optimize this. So I'm going to run this. I'm going to run this. What's it? Polymorph, right? And I would show you that if I don't pollute the profile, it actually runs really fast, pretty fast. But I will pollute the profile. Actually, maybe I should show you that without the profile pollution, it runs really fast. So we're gonna remove this program argument, and now we will not pollute the profile. Our lengths will be 0. We will not pollute the profile, and it runs in 3 seconds. Excellent. Now we will pollute it, and it will run slower. How much slower do you think it will run? 2 times slower. I don't know. I don't remember the result for this one. Yeah, approximately two times slower. So it ran for 5 seconds. Why? Because this pollute profile loop is 2,000 iterations. So it doesn't contribute that much to the actual runtime. What contributes to that runtime is that here we cannot inline efficiently because we don't know which method to inline. And we execute this loop many, many times. So I will run this now with the... How did I run this, actually? Yeah. I will run this... Oh, boy. That was with Graal. 5 seconds with Graal. So without Graal, it should be slower. It is slower. Something is not right. Wait. Don't use JVM compiler, pollute the profile, run on the GraalVM, run. Surprising. I had different results, I think. Wait, let's try with Graal again. So now, let's see plus, use JVM compiler. It is a little bit slower. I expected a larger performance difference here. Not sure what's currently, but we'll move forward because I want to show you a couple of other things. So what happens is that we cannot inline efficiently here. What we can do is we can say that we would like to increase the profile width of how many implementations we can inline. By default for C2, I think it's 2. So there is a, like when 2 implementations sit in lines properly, we can increase that number, and then it should run more efficiently, I think, kind of like 5-second things approximately. Wait. So I'm going to disable this. So I will show you that it uses the C2, and I will say that please increase the amount of Kali implementations that it can run. And you can see it runs really fast, which is very weird because I expected it to run the same way with Graal. Figure it out later. However, important bit here is that you can configure C2 for some cases to run faster as well. Now, if we change this, So if we replace this implementation with where there is no single dominant implementation. So previously, in our main loop, we just used one operation, right? So despite polluting the profile, we had one implementation that was always running in the main loop. So now we will change that. And now, even increasing the width of the profile should not be possible, should not lead to that. Should be slow again, 5, 6 seconds. Should be, right? It runs for 5 seconds already. 10 seconds, excellent. So now, I will disable this because I will run it with Graal. Now it should be faster than 10 seconds, hopefully. Tried yesterday, it was faster. Come on, 1, 2, 3, 6 seconds, excellent. So changing the amount of dominant implementations doesn't actually lead to decreased performance on Graal, which is quite fantastic. So other things, so this is the polymorphic inlining, which is great if you use collection libraries. Any program that uses different implementations of lists could potentially benefit from a more advanced polymorphic inlining. Also, normally inlining is also kind of more sophisticated in the Graal compiler, but it's rather hard to show because the inlining is just like taking code from one place where we call and avoiding the virtual call there, or actual call, and just copying that into the caller. So it's just not easy to show with a single benchmark what's happening with that code. However, I want to show you the final benchmark here. Not the benchmark, the implementation of a thing. And this is a very interesting one to me. So, which combines those things kind of together. And actually, what it tries to show that you can write code as you want and still not suffer the performance degradation. I have a benchmark here, 2 benchmarks that computes minimum of 2 numbers. And one just computes whether A is smaller than B and then returns AB. This is how normal people write minimum. And the other one is somewhat artificial. So we take a factory, which is a factory object here. We get a weird comparator from that factory. So we create this weird comparator, very enterprisey. And then this weird comparator computes minimum by creating an array of numbers and then sorting them with bubble sort, and then returning the first one, which is technically the valid way to find the minimum, but not something that you would write on the first try if you asked about how to write a minimum. But you certainly can do that. So we're going to run this without the Graal compiler first. Configurations, probably just, yeah, min. And we will disable the compiler. We'll remove this, and we'll run. Hopefully, the numbers here will be kind of similar to what I saw yesterday. So I will be able to talk about it and not be very surprised. So it's going to run for 2 minutes. Excellent. We have 3. So that means we can almost run it twice to show the results. What I want to show with this benchmark, actually, is that with a sufficiently advanced compiler, there should be no performance penalty for writing highly abstracted code like this. Because when you normal Java developers, you write normal enterprise applications or microservices or something, most probably you deal with abstractions. You deal with your objects, you deal with your Hibernate proxies, you deal with your other proxies that your annotation processor generates for you. You use your factory classes, and you use your different implementations for authorization primitives, right? You write user-level code. You very rarely write matrix multiplication or low-level bit shifting. Who writes bit shifting in matrix and math and things daily, weekly? Some people do because, well, most probably they write frameworks or something, but essentially they do write that, and it's an important thing to be able to write. Come on, do this. you can see that actually the C2 does a decent job at optimizing this. So the normal one, the minimum one, was 2 nanoseconds per operation. And this weird one is something like 4.5. So slower, twice as slow, but maybe not incredibly slower. I would expect this to be a little bit slower, actually, normally. If somebody would ask me, what's the performance degradation of this code versus this code, I wouldn't say like 2x. I would say that this is ridiculous. But this is the numbers, and I will run the same with Graal now. And hopefully, it will wait, this. So this, like, to be honest, this didn't use the JVM compiler, right? Because the JMH. Now we'll disable this line. Excellent. And then we'll rerun this. So now it will run with the JVM compiler. Excellent. So now we are running with Graal, cooking with gas, so to speak. So what I want to show is that you can run complex workloads using the normal application level code and not worry about performance. And, well, you should worry about performance. You should be aware of the performance. But you don't need to worry about how to modify your code to make it compiler friendly. At some point of time, yes, if you are into high-frequency trading or anything that low level that it multiply matrices, or that it's really, really important for that particular bit to be super optimized, yeah, you can do manual optimizations. You can mangle the code readability for performance reasons. But normally, you shouldn't be able to. You shouldn't do that. And I would expect that normally you don't do that, which means that there is quite a large chance that maybe with a more sophisticated compiler that is great at the escape analysis, polymorphic inlining, normal inlining, and other optimizations, maybe your code will run faster. Are we there yet? We're not there yet. However, so you can see that for this minimum one, it runs a little bit slower with Graal compiler. Not sure what's happening there, but before it was 2.1 or 2.2. Which also shows that it's really hard to beat JVM when your methods are really small and very nicely inlineable. When you write code like this throughout your application, it's really hard to beat C2. But what I wanted to show you, that the difference between minimum 1 and minimum 2 is actually very small. That is using Graal. So Graal optimizes all this creativity. It optimizes it all away. And actually, it runs the code as you would expect it to run from a sophisticated just-in-time compiler. So we are out of time. So what I will show you is that you should check the project out. It's great. It's written in Java, so you can understand. You can contribute things if you want. You can try it on your workloads. You can try it on your test workloads, your benchmarks. We think, GraalVM team, we think the project is ready for industrial adoption. It's ready to run workloads in production. We are running some applications internally using the GraalVM distributions. Twitter is running using the compiler. Not our distributions, but they have the compiler from there. If you try it, the more you try it, the more we know that it actually is ready for the prime time, or the more bugs we have to fix. And the team is really, really excited about fixing all kinds of issues, because there haven't been that many compiler bugs as of lately. You can follow us, you can find us, you can ask us questions, you can ask actual maybe more low-level explanations of how it does things or how to investigate what it does. But building a universal virtual machine and the best-in-class just-in-time compiler is a community effort. So it would be really cool if you check it out. It will make me personally very happy. Thank you.